Next, we're gonna study a way to estimate the relationship between variables that can be used to estimate, for instance, the multiplier that we studied in the previous chapter. This method is much more general than that. In fact, we can use this method to estimate the relationship between two variables or among many variables. In many different cases, it's used in many applications, but we are gonna use an example here that is related to the estimation of multipliers. I invented an example here. The county of Echo 610 has 25 census tracts. Using GIS, an economic developer practitioner already estimated the exports and already collected the data on total income for all of the tracts. How would you go ahead and calculate that? Well, it is similar to a homework that we already did. I'm going to open my example of the homework here. So here we are. Let's look at motor vehicles, for instance. 75,000 is supplied and 38,000 is demanded. More is supplied than is demanded. So what happens to the rest? Well, the rest is exported. Think about it. If $75,000 were sold, but only 38 were purchased by people in the region, that means that the rest, which is 36,000, was exported. In fact, to calculate total exports in the tract, I would have to add up everything here that is in red. Red, we have exports. If you add for every single sector, that is a way to calculate total exports for the region. Now, I am assuming in this example that I invented that the economic practitioner already did that for every single tract. Now, what we want to estimate is the multiplier. Remember, in chapter 5, we derived the equation total income equals multiplier times exports. And the multiplier was 1 divided by 1 minus little c, where little c is the propensity to consume locally. So this little k here, the multiplier, is what I'm going to estimate. Now I invented some data here for my fictional county. This is the data for income of every tract, so there are 25 tracts, and this is the data for exports for every tract. Okay, so in the first tract, income is 49,000, export is 19,000. The first model estimate is in the multiplier in its easier form, the one we saw last chapter. Now, let's see how I can use econometrics to estimate this model 1, which I'm calling model 1. Let's go to Excel. Okay, so here's the data that I invented. And the first thing you have to do is you have to go to File and make sure that in your options, go to the add-ins, that you have the Analysis Tool Pack. I am not going to click it here because I already have it. If you don't have it, you go ahead and press Go, and then you press OK. Now, the Analysis Tool Pack, to use it, you go to Data, and there's Data Analysis here, the last one. I'm going to choose Regression here. Okay, first, I'm going to input the Y range. The Y range is my dependent variable, as we're going to call it, the variable that is on the left-hand side. Then, I'm going to input the variable that is on the right-hand side. It's called the independent variable. The labels or the name of the variables are here on the top, so I'm going to check here. And my first model has no constant. We're going to talk more about that later, so I'm going to click here, constant is 0. Press OK. Here are the results. You take a whole semester in econometrics just to start talking about how to interpret these results and to explain where these results come from. But let's see the main parts of this output here. I copy and pasted part of the output. Look that the intercept is 0. That's because we assume no intercept. There is no intercept in this model. Now, the coefficient is 2.4999. What that means is this is your estimate of the multiplier. The multiplier is 2.499. Notice that I invented this data. That's why this regression is so good. The data that I invented, the real multiplier is 2.5, and you can see that Excel did a very good job in guessing what was the true value of the coefficient. Again, in real life, you don't know the real coefficient. I know because I invented this data. So the result here is very close to the true 2.5 multiplier. Now, how do you test the quality of that estimate? One way to look at it is to see the t-statistics, this column here. Whenever the t-statistics is larger than 1.96, that means that the coefficient is statistically significant at a 95% interval. Now this is much larger than 1.96. Again, I invented the data, so I invented a very good data. So the quality of my regression is extremely high here. Another way to see the quantity of the regression is by looking at the p-value. The smaller the p-value, the better the estimate of the coefficient. In this case, this number is actually has 113 decimal cases here. So that's a very good quality estimate. Here we have the 95% interval. So in 95% of significance, the real estimate is between this number and this number. And you can see that 0 is not here. When 0 is not in this interval, we say that it's statistically different from 0. That's what it means, statistically significant. Again, don't worry too much about it. If you take a whole semester to explain everything, just make sure that before making any conclusions, your t is large enough. Okay, let's redo the model, but let's include a constant in the model. Now I'm assuming that income is a function of exports, but I'm going to put a constant here. Let's go back to Excel and re-estimate the second version. Okay, here I am with my data again. I'm going to go back to data analysis, regression. I already have the data set up here, but now I'm not going to do constant is 0. I'm going to assume the model actually has a constant. So let's run. And here's my new output. So let's go back to the PowerPoint. Now, Excel estimated an intercept. However, the t-statistic of the intercept is smaller than 1.96. In this case, it's negative. So I would have wanted the absolute value to be smaller than 1.96. The t-statistics can be negative. Then I have to look at the absolute value. Now you can see that the t-statistics of the intercept is small. The absolute value is smaller than 1.96. And in fact, if you look at the 95% interval, 0 is contained in it. Therefore, I cannot conclude that my coefficient of K0 is statistically larger than 0. And in fact, since I invented the data, I know it's equal to 0. So again, Excel did a good job in indicating that, hey, there may be not a real intercept in this model. My estimate of the multiplier is 2.49, again, very close to the true. So this model is well specified. This constant here is 0, and the multiplier is 2.49. Now let's do a third model. Assume now that you have employment data, the same imaginary county, and you're going to use employment data to calculate the multiplier. Remember, this is basic employment, which is the same as employment where the employees are working on products to export, and this is total employment. But a model is a simplification of reality. In real life is way more complicated. Even though the model gave us the simple equation here, you may think, no, in real life that's not the case. For instance, one may argue that in real life, the effects of export employment in certain sectors affect total employment more than in others. So here's model 3. Now total employment is going to be a function of a constant, export employment in manufacturers, in agriculture, and in services. So basically I'll be estimating 3 multipliers, and then I can compare them with each other. So let's go to Excel again. I invented this data. I'm here in module 3. So I'm going to run a regression again. Data regression. Now, this is my dependent variable, the one in the left-hand side. I'm going to have to redefine here my independent variables because now I wanted to include 3. Constant is not 0. Labels, because I have labels in the first line. There you go. Here's my data. I copy and pasted each of the PowerPoints. Okay, so here are my estimates of the multipliers. The intercept is again not different from 0. That's because when I invented the data, indeed, there was no intercept. This is the multiplier for the manufacturing employment, for the agriculture employment, and for the service employment, all these export employment. So you can see that they have different multipliers. What that means is the following. If I increase export employment in manufacturing sector by 100 employees, I'm going to increase total employment by 150 employees. So that's the specific multiplier here. It has to do with what in the last chapter we call sectoral multipliers, if you want to review that. Now this t-statistic is low, but all the t-statistics of my multipliers are high. So that's a very convenient way to estimate the relationship between different variables. In summary, what do I have here? First, I needed independent variables. Those were the export employments. Those are the variables that we assume are affecting the dependent variable, which was total employment or total income. And then the other component is the parameters, which is what we are actually estimating, the things we are trying to figure out, which is the relationship between the variables. There are some problems with this technique, though. All sorts of statistical requirements must be true for the model to be valid. The first is pretty obvious, linearity. I am modeling the relationship as linear. The second is the exogeneity of the independent variables. Remember last chapter, we assumed that exports were exogenous, determined by the behavior of the regions around our region. If that's not the case, I cannot explain an endogenous variable as a function of another endogenous variable. All my coefficients will be wrong. Also, we make a lot of assumptions about the error term. It is never the case that this is exactly true. There's always going to be part of the total employment that is not explained by these variables. That's called the error. We assume that the error behaves in a certain way. That is usually not true. Now, finally, parameters, estimations based on past observations. Relationship among variables change all the time. In summary, I cannot explain all that is to know about econometrics. That will take more than one semester. Here's a to-do list for you to run a regression and understand when the variable is significant or not.